In the last lecture, we will talk about non-parametric tests. Previously, we focused on statistical tests that assumes the data follow some common distribution, such as the normal distribution. Thus, if the data violates the assumptions, then the tests may not give us valid results. Non-parametric tests are distribution-free and thus can be used for any data. For example, non-parametric tests are frequently used when the population data is not normal and the sample size is not large enough. Also, if we have categorical data with only frequency and would like to know if it is different from our expectation, there are several factors may determine if we are more interested in parametric or non-parametric tests. First, non-parametric tests can be used for data that do not follow common distributions. Second, most parametric tests test the mean, and most non-parametric tests test the median. Last, many parametric tests have greater statistical power than their corresponding non-parametric tests. The table below shows the non-parametric tests that may be used instead of their corresponding parametric tests. For example, we may use Fisher's sign test or Wilcoxon's signed rank test to find if the median is at the expected value or if there is a difference between the two paired samples. Chi-square test and Fisher's exact test may examine if the outcome proportions are the same as our expectations. Mann-Whitney U test may be used to test if the two independent groups are equal. The Kruskal-Wallis edge test is the non-parametric version of one-way ANOVA. Trees, k-nearest neighbors, splines, neural networks, etc. are the widely used machine learning methods that may even provide better estimations than linear regression. We don't cover machine learning methods in this lecture series, but we will discuss other non-parametric tests here. Both sign test and signed rank test may be used to test if the median is significantly greater than or less than a specified value. The paired test may be treated very similarly, since we may use the difference as a derived sample and do one sample test. The sign test is a simple non-parametric test with the assumption that the data is from a random sample. The null hypothesis is the median theta is theta 0. We count the number of values that less than theta 0 as NL and that greater than theta 0 as NG. The statistic is the lesser of the NL and NG, which follows a binomial distribution with the probability of 0.5. The Wilcoxon signed rank test has an additional assumption that the population distribution is symmetric in addition to random sample. The null hypothesis is the same as sign test. It ranks data by the absolute values from the non-zero smallest and add signs back to all ranks. The statistic is the sum of all signed ranks, which follow a distribution cannot be described by a simple function. But for large samples, the distribution converges to a normal distribution with this mean and the standard deviation. Please notice in both tests, the sample size n does not include data at theta 0. In sign test, n is nl plus ng, and in signed rank test, n is the number of observations with rank. The chi-square test is a very useful test that may be used to find out if the data are consistent with the distribution as goodness of fit. If there is a significant association between two categorical variables as independence, or if two or more populations are equivalent as homogeneity. For example, we roll a dice 100 times and we are expecting a uniform outcome. The test results may let us know if the dice is fair. This is a goodness of fit. We randomly select 200 people and study if there is any association between education and gender. This is independence. If we modify the design and randomly select 100 males and females separately, we may study if male and female have same distribution on education. Then we have homogeneity for a very similar research question. Thus, we know that the main difference between the independence and the homogeneity is the experimental design. The assumptions of the chi-square test include a random sample. The data should be able to summarize in counts or frequencies, and all counts should be sufficiently large. A common practice is all counts should be larger than 5. The null hypothesis of the chi-square test is no significant difference or association. The test statistic is chi-square, which is the sum of this term, where OI is the observed number and the EI is the expected number derived from the null hypothesis. Fisher's exact test may also determine if there are associations between two categorical variables. In addition to the assumption of the random sample, the test is normally one-tailed due to the procedure. It can be used for data where the expected number of counts is small. For a 2x2 contingency table as this one, the probability of obtaining the observed counts under the null hypothesis may be calculated using the hypergeometric distribution as this formula. After we sum over all probabilities that are as extreme or more extreme under the null hypothesis, we have the p-value. The smaller the p-value, the greater the evidence for rejecting the null hypothesis. We may use an example here. 25 students take 2 exams. 4 students failed in the first exam, and 5 students failed in the second exam. We would like to know if the second exam is more difficult than the first one. The contingency table is shown here, and we may use the Fisher.test function in R for this problem. The calculation is based on the odds ratio, and the p-value is 0.016. Thus, we will reject the null hypothesis and suggest there is enough evidence to claim that the second exam is more difficult than the first one. The Mann-Whitney U test, also known as the Wilcoxon rank sum test, is able to compare two populations. In addition to the random sample, The test requires the dependent variable to be continuous, or at least ordinal, so that it can be ranked. If the two population distributions have different shapes, then the test determines whether two distributions are equal. But more commonly, the test determines whether there are differences in the two medians if we may assume the two distributions are the same shape. There are two methods to calculate the test statistic U. The first is the direct method for small samples. In this method, for each unit of one sample, we count the wins over the other sample and sum the counts in each sample. For example, if we have two dice and roll each dice 5 times and get 1, 2, 3, 4, 5 for one dice and 2, 2, 3, 4, 5, 6 for the other, the outcome may transfer to wins as this. Ties are counted as 0.5 win. For example, 4 in sample 1 has 2 wins and 1 tie. Thus, it has a count of 2.5 wins. The sum is U1 and U2. Here we have U1 is 9 and U2 is 16. The second method is the indirect method for large samples. In this method, we rank all units in both samples and use the formula to calculate the statistic U. Here, R1 and R2 are the sum of the ranks in two samples. In the example, we may rank the outcomes from the smallest and the largest outcome. 6 has a rank of 10. After we sum in each sample, we have R1 is 24 and R2 is 31. Using the formula again, we have U1 is 9 and U2 is 16. The test statistic U is the lesser of U1 and U2. Again, we do not have a simple function to describe the sampling distribution. Fortunately, for large samples, the statistic U is approximately normal when the mean as n1 multiply n2 divided by 2 and the standard deviation is this if there is no ties in the ranks. This slide is an example of the Mann-Whitney test. We studied the example in lecture 10. We would like to know if boys and girls have different exam performance. Sample 1 has 20 boys' exam scores and sample 2 has 20 girls' scores. The two samples are independent. Two parametric methods are used previously. Pooled t-test for equal variance and Welch-Satterthwaite t-test for unequal variance. Both methods give a p-value of 0.04. Here we use the Mann-Whitney non-parametric U test, and we have a z-score of 1.8, which gives a p-value of 0.07 for a two-tailed test. The non-parametric test indicates that the exam scores are not significantly different. Obviously, t-test and u-test give different results. The sample data may not tell that which test is more accurate. First, the t-test tests the mean and the u-test tests the median. Second, the size may not be large enough to validate the central limit theorem. The normality assumption may depend on the population distribution. The Kruskal-Wallis test, also known as H-test or one-way ANOVA on ranks, is a non-parametric test that may compare two or more populations with equal or different sample sizes. Thus, it is an extension of the Mann-Whitney U test, which only tests two populations. So, the two tests have the same test assumptions. If the data contains no ties, then the test statistic H may be calculated by this formula. For large samples, the statistic H approximately follows a chi-square distribution with k-1 degrees of freedom. Like the Mann-Whitney test, the Kruskal-Wallis test requires a large amount of computation power to find the exact probabilities. In summary, we discussed some common non-parametric tests. Different from parametric tests, non-parametric tests can be used when the data do not follow common distributions, such as the normal distribution. There are several differences between parametric and non-parametric tests. In addition, most parametric tests test the mean, and most non-parametric tests test the median. Also, many parametric tests have greater statistical power than their corresponding non-parametric tests. We introduced some common non-parametric tests. Fisher's sign test or Wilcoxon's sign the rank test may check if the median is at the expected value or if there is a difference between the two paired samples. Chi-square test and Fisher's test exact test may examine if the proportions of the outcome are the same as our expectations. Mann-Whitney U test may test if the two independent groups are equal. The Kruskal-Wallis H test is the non-parametric version of one-way ANOVA.